all right. I'm still trying to get things sorted out.
Sorry. So guys, you're gonna grab your stuff and we're gonna go downstairs.
No, I'm not going to do that.
It's like a whole lot. They have modules for everything. Science, math, history, languages, computer, and what it is
They're actually already answered. Yeah.
it's a thing like a series of maybe like 10 videos
There's nothing else left here.
telling you about Khan Academy.
Oh, okay. Yeah, no, it's good. I remember it Thank you very much.
I'm gonna try maybe like watch 1 or 2 videos.
Yeah.
Yeah, we all way ahead of you.
Yeah, did he tell you like you cross off like a week?
Yeah, I left the week after she came.
Yes.
I was working as a so I worked at a private school. Where's the school? It's not so galvanized. It's, well, the area is called Hudson Square. It's kind of like school. Okay. Did you enjoy that? I did, yeah. Just like, right now I actually want to go back to it. Last week. Okay.
Oh, that's
So one thing I should have pointed out last time about our notation is something like for 2 spins, this operator IZ, it came from the direct product of IZ with the identity operator for the S spin. And I told you that we don't, even though you would think that we would. You might think that our language would say that we should put an S down here. We should. That there should be an S there, should be the identity operator for the S spin. We never write that. And then here, you might think that this should really be IZE, because it's the direct product of the single spin IZ operator with the identity operator for the S spin. But we usually don't write that either. So you have to know, again, from context, that there's always some identity operators floating around, that you can insert them when you need to, and you need to put them in the right place. So, for example, you will come up that. for example, it'll come up that sometimes when I have an IZ operator, I'll want to think about it as being IZE, and then recall that I could write IZE as S alpha plus S beta. Right, where these were the operators that we talked about yesterday, where S alpha would represent the population of the S alpha state, and S beta would represent the population of the S beta state. But I have to know that if I want to do that, that the E goes in here, and because it's in this position, I need E sub S, so that I put S alpha and S beta, because I beta plus I alpha is also the identity operator. It's the identity operator for the I spin, and it wouldn't make any sense for me to write, for a spin 1/2 particle anyway, IZ times I alpha plus I beta. So kind of the precise meaning of these symbols kind of grew up a little later than people got used to writing the symbols themselves. So you could view the notation as being a little bit compact, and you have to be a bit of an expert to know where to put in identity operators when you need them, or you could view it as we just made a mess of the notation and have to patch things up after the fact. But particularly when talking about J-coupling or Troisi effects, this trick of inserting the E and then writing it as the sum of the alpha and beta states gets used all the time. I could, for example, also do, for example, write E, the identity operator. It's also, right, E times E. Or I could think of that as I alpha plus I beta, S alpha plus S beta. And when I multiply those four terms out, I'll have I alpha S alpha, I alpha S beta, I beta S alpha, I beta S beta. And those would represent the populations of the four states. The alpha alpha state, the alpha beta state, the beta alpha state, and the beta beta state. And they all add up to unity because, again, the populations are conserved. And while I'll write the operators and the wave functions in an ordered fashion, I and S, for example, for I1, then I2, then I3. In fact, the operators for different spins commute with each other. So if in some calculation we need to swap an IZ and an SZ, we can do that. We can't swap an IX and an IY, but we could swap an IX and an SY. So different spin operators for different spin types commute, but the operators for a given spin don't necessarily commute. So that was to patch up a bit from the other day. And now that we can generate operators for two spins, we can then write down the Hamiltonian for the scalar coupling. So the scalar coupling Hamiltonian, or I should always say the isotropic scalar coupling, because this comes, again, what solution NMR spectroscopists call J, the scalar coupling, is really the trace, or the average of the trace of some tensor, just like the isotropic chemical shift is the average of the trace of the chemical shift tensor. And we'll leave dealing with tensors for Ann, because for solid state NMR, for solution NMR, we won't need really to worry about the tensors until we get to relaxation. Whereas solid state NMR, the tensors come in right from the beginning. But this means the average of the trace of some tensor. And it'll turn out that we can always write the Hamiltonians as a product of some operator, a tensor, and then some other operator, and then manipulate from there into a form that we need. So there's other parts. The full Hamiltonian would have other parts from the tensor, but they're not important in solution, so I didn't write them down. So this says then that the Hamiltonian is J, which is measured in hertz conventionally. It's multiplied by 2 pi, so that we have angular units. And then we have the dot product of the operators for the I spin and the J spin. And we would sum over all possible pairs where they have a non-zero J coupling. But again, importantly, there's only pairwise interaction. So we only have J coupling, say, spin 1 and spin 2, and not simultaneously spins 1, 2, and 3 with one coupling. We could have a coupling between spin 1 and spin 2, a coupling between spin 2 and spin 3, but those are pairs of pairwise interactions. There aren't any 3-spin terms. In solution, one of the reasons one moves to bigger and bigger magnets is that the J coupling is independent of the size of the magnetic field. It's a property of the molecule. But the chemical shifts are all proportional to V naught. And so if we go to a larger and larger field, measured in hertz or angular units, the frequency difference, for example, between an alpha hydrogen and an amide hydrogen keeps getting larger and larger. In parts per million, it's unchanged because parts per million is a relative measure. But the difference, say, 4 parts per million on a 500 is 2,000 hertz. But on a gigahertz machine, it would be 4,000 hertz. And what's called the weak coupling limit is the situation where the scalar coupling frequency is much less than the frequency of the resonance frequencies of the 2 spins that are coupled together. So if we have an amide hydrogen and an alpha hydrogen, they're separated by something like 3 or 4 parts per million. So that would be, let's say, 1,500 hertz on a 500 megahertz spectrometer. And then the question is, how big are the J couplings? So proton-proton J couplings, a big one is 15 hertz. So the chemical shift difference is 100 times larger than the J coupling. And that would be what's called the weak coupling limit. The shift difference is much larger. If we talk about the heteronuclei, for example, a 1-bond carbon-hydrogen J coupling is maybe 150 hertz, but the difference in frequencies between carbon and hydrogen is, on a 500, it's 375 megahertz. The frequency difference is just gigantic. So the heteronuclear couplings are always in the weak coupling limit. But even the homonuclear couplings on large enough magnets get into the weak coupling limit. And if we're talking about 800 megahertz spectrometers and above, really the only weak couplings left in proteins, couplings that are large enough that they're comparable to the frequency difference, would be carbon-carbon couplings in the aromatic side chains, like phenylalanine. Some of the chemical shifts, say, between the delta and epsilon positions in the ring can be very small, and therefore comparable to the couplings, which might be 30 to 50 hertz. So that's one reason. If you look at, if you just look at a bunch of solution NMR papers, frequently there are rather minimal assignments of the aromatic side chains. And part of that is that some of the experiments that rely on weak coupling limits don't work so well, because some of those spin systems won't be in the weak coupling limit and wants to do more complicated things. And frequently, graduate students wanting to graduate figure they'll do those complicated things for the next postdoc on the project. So in the weak coupling limit, the only part of the Hamiltonian, again, if we're interested in first order spectra, so first order spectra, where the resonance lines are, what the multiplet structure is, not the line length. If we're just interested in first order spectra, the weak coupling limit, we only need to keep terms in the Hamiltonian that commute with the Zeeman interaction, that commute with being off, or the z-axis. So in this Hamiltonian, I dot j, right, I want, let's say IS. I dot s would be IX SX plus IY SY plus IZ SZ, same as a dot product for a vector. And if we're in the weak coupling limit, we can throw away the IX SX terms and the IY SY terms. Or in this case, the I1X, or I sub IX, I sub JX, and I sub IY, I sub JY, and just keep the ZZ terms. And that's shown somewhere. And that's shown here. We've only kept the ZZ parts. And again, when Ann comes, she'll talk a great deal about, in solid state, what's called truncation, when you can throw away terms in the Hamiltonian that don't commute with the B naught field, with the big Z field. And here, we throw them away because we're in this weak coupling limit. Later on, we'll see that there are experiments where we try to restore the strong coupling limit. But for right now, we're happy to be in the weak coupling limit. So then, we have the Hamiltonian for the scalar coupling, and we just have to add it on to the scalar coupling for the resonance frequencies. And notice, in this case, the shift evolution Hamiltonian depends only on Z operators, and the coupling Hamiltonian depends only on Z operators. And that means these two Hamiltonians commute. And since they commute, it doesn't matter what order we work out the answer to the problem. So we can work out what happens to the chemical shifts, and then work out evolution under the scalar coupling, or we can work out evolution under the scalar coupling, and then, oh, that's not a good sign. And then go back and do the other bit of the Hamiltonian. I think this actually means we've lost the internet connection. No, the internet connection is there. have to go back to doing it the old-fashioned way. And that's a huge simplification. The fact that in the recoupling limit, the chemical shift and scalar coupling Hamiltonians commute means we'll be able to do a large number of problems analytically by hand. When we get to the case where parts of the Hamiltonians don't commute, we either have to do computer simulations or start doing approximations, such as average Hamiltonian theory, which eventually we'll come to. So now we don't have a pointer. So here's our propagation forward, some starting scalar coupling, or starting density operator, and now the Hamiltonian is independent of time, so we know the solution. It's this kind of sandwich of operator terms. And I plug in the J coupling Hamiltonian, and it's conventional for us to move this 2 that I had here as part of the 2 pi over here to make 2IZ SZ, because remember that factor of 2 appeared when I generated the operators in order to keep the operators normalized relative to each other. So it turns out to be convenient to use that factor of 2 that was already there in the expression to account for the normalization. And now we have to figure out what this means. What does it mean to take the exponential of this new operator or this new matrix? And we do the same thing that we did before. We expand in Taylor series and then work out term by term what the matrix products are, and then try to sum the series. And when we're done, we'll find out that this exponential is equivalent to the identity operator times cosine of the scalar coupling evolution divided by 2, and then something that depends on this 2-spin term, IZSZ, with a sine component. And here's what the matrix looks like with S defined in this way. So once again, we have a matrix representation of the operator, so we can do the calculations by multiplying the matrices together. I have a matrix for sigma, I put it in here, and then which way did I do it? So this matrix would go here, and then the complex conjugate of this matrix would go over here, and then I multiply them all together, and then try to figure out what the answer is. And of course, if we do that for a while, we find that there are rules, and the rules look like these same pictures again, where I have 3 axes, and now the axes are labeled in an even more peculiar way. The Hamiltonian is proportional to IZSZ, so I put that along the z-axis. And then I put IX and IY in order that I have a right-handed coordinate system. So X has to rotate to Y. And now what's different is one of these 2 axes gets decorated with an SZ. And you can see I could do it one of 2 ways. I can put the SZ here, or I could put the SZ over here. And which way I do it depends on the problem that I have. So suppose I have IX magnetization, and I want to know what happens to IX magnetization under the scalar coupling Hamiltonian. So I have IX, so I want this to be IX. And that means the decorated axis has to be the IYSZ. And I put the factor of 2 there for this normalization. And now my thumb goes along Z, my fingers are on IX. As I rotate, the IX magnetization will be converted into 2IYSZ magnetization. So that I have IX will be modulated by cosine pi JT, and 2IYSZ will be the sine pi JST. So it's completely analogous to the pictures for chemical shift. The starting axis gets the cosine modulation, and the destination axis gets the sine modulation, and I figure out which axis using the right-hand rule. If for some reason I had this magnetization, and I want to know how it evolves, then I would start here, and it'll evolve back towards minus IX magnetization. Or if I want to know what happens to IY magnetization, I then decorate the x-axis with the SZ, and IY will evolve towards the minus 2IXSZ. So it would be very handy at this point to have unfortunately, we need the board, and I'm not sure. So let's forget about mathematics for a moment, or most of the mathematics. When you have, suppose we have an amide hydrogen, and it's coupled to a nitrogen 15. If I look at the amide hydrogen spectrum, what's the multiplet pattern that I see? You see a doublet. Right? You've done, everybody who's made an N15 protein knows that you see a doublet in the 1H spectrum. And we call the splitting J, right, in Hertz. And this means, right, that there was, and these two lines have equal intensities, for reasons we'll talk about later. They have different line widths, so one is shorter than the other. But ignoring that, if we did this in a very small molecule low field, these are equally intense. And it turns out that this, so here we have our NHs, in solution, half to a very, very good approximation to within something like 10 to the minus fifth accuracy, 1/2 of the nitrogens are in the alpha state, and the other half of the nitrogens are in the beta state. And there's a slight interaction between the spins that shifts the frequency of the hydrogen. It shifts the frequency of the hydrogen by either plus J/2 or minus J/2. And then it turns out that these are the hydrogens whose partners are in the beta state, and these are the ones whose partners are in the alpha state. Depends which ones are which, depends on the sign of the coupling and the sign of the gyro magnetic ratio. So I think this is right for nitrogen, but it doesn't matter. The main point is one of the multiplet components represents the partner spin in the beta state, and the other multiplet component represents the partner in the alpha state. And suppose we are on resonance with the chemical shift. The chemical shift is right here in the middle. And if we were on resonance, we'd see no chemical shift evolution. And we'd only see the scalar coupling evolution in the spectrum. So what happens? Well, we start with IZ magnetization. But now I can play my game. Since I'm interested in the scalar coupling, the IZ magnetization, right, is IZ S alpha plus S beta equals IZ alpha plus IZ beta. IZ S alpha plus IZ S beta. Right, using my trick that this is the identity operator, and this tells me my Z magnetization, half of the I spin Z magnetization is connected to an S spin in the alpha state, and the other half of the IZ magnetization is connected to an S spin in the beta state. Now I do a 90-degree pulse. Let's suppose I do a pulse along Y. After the 90-degree pulse, I have IX magnetization, but I now recognize that that is also IX S alpha plus IX S beta. And now the magnetization will start to precess. But if I look at this picture, the magnetization whose partner spin, this should be an S alpha, whose partner spin is connected to S alpha, should precess at plus pi j over 2, or plus j over 2 in hertz. And this one should go at minus j over 2. So let me relabel these. So really I have, let me look down from the top now. Looking down from the top, I have the x-axis, the y-axis. I've created IX S alpha let me call that beta. And IX S alpha. And now, precession, this will precess in this direction with frequency plus j over 2, or in angular units pi j, if I multiply by 2 pi. And this one will go in this direction at minus j over 2, or minus pi j. So that the difference between the two frequencies is j in hertz, or 2 pi j in angular units, back to what you expect from the spectrum. And what happens if I wait until they come to the y-axis? Right? They're rotating at the same rate, just in opposite directions. So there's going to be a time when this is here, and this one is there. Right? Everybody agrees if they rotate in the same rate in just the opposite direction, eventually they'll be anti-parallel along the y-axis. And what is that? Well, this now, what I'm left with, back to blue, would be minus IY S beta, because we're pointing along the minus y-axis, plus IY S alpha, pointing along the plus y-axis, and this is equal to Iy S alpha minus S beta, which is the same as 2 Iy 1/2 S alpha minus S beta. And this is what I just called SZ. Z magnetization is the difference between the population of the alpha state minus the population of the beta state. And if you look back at the definition of the operators in the beginning of yesterday's lecture, there was a factor of 1/2 introduced in front of all of these two spin operators. So I put the factor of 1/2 in. That's SZ. So this is 2 Iy SZ, which is my symbol here. So my symbol here reflects the state where the two doublet components have precessed to where they're opposed to each other. They're 180 degrees out of phase with respect to each other. When the two doublet components are in phase, we call that an in-phase operator. So Ix is an in-phase operator. The two doublet components are in the same sense. It's S alpha plus S beta. It's the identity operator. If we recorded the spectrum, we would see the two doublets standing up. The antiphase operator, the two doublet components are now opposed to each other. And if we recorded the NMR spectrum, the two doublet components are going to be 180 degrees out of phase. If we phase to be up, the other doublet component will be down. And we call that antiphase coherence or an antiphase operator. So these symbols, which I derived just by these direct product manipulations of the one-spin matrices, reflect exactly what you already knew happened in the NMR spectrum. And that's why this theory is so powerful, that every feature in the NMR spectrum is associated with these kinds of mathematical symbols, so we can manipulate the symbols in order to understand the NMR experiment. And more interestingly, if we manipulate the symbols in some novel way that looks interesting to us, there then must be an NMR experiment that exhibits that phenomenon. So if you are noodling around on paper and suddenly realize, oh, aha, if I was able to create this operator, it would be an interesting NMR spectrum, then we usually have a recipe for designing the experiment that would generate that NMR spectrum. What would we have to do here to generate this, for example? We've now seen, aha, if we apply a 90-degree pulse and wait a little while, we'll generate this antiphase coherence. How long do we have to wait? Well, we want this evolution, which goes, for example, the green doublet component evolves as pi j in angular units for some time. And what do we want the net angle to be? How much do we want this to rotate by to bring it to the y-axis? Pi over 2. And the pi's cancel. So t is equal to 1 over 2j. So if we know what j is, which we can always measure from the spectrum, the simple one-pulse spectrum, we can calculate how long the delay needs to be. So now I have an experiment where I apply a 90-degree pulse, and then I need to wait a delay t equal to 1 over 2j, and then I record the spectrum. Rather than starting to record the spectrum right after the pulse. Right after the pulse, I have IX magnetization. The two doublet components have the same sign, so I'll get this normal spectrum that will look like this. I wait this amount of time, and then I turn on the receiver. I'm going to get the antiphase spectrum, except it's going to look like a mess because of all the chemical shift evolution. Because during this time period, there'll be chemical shift evolution, right, as well as scalar coupling evolution. So there's going to be a gigantic phase error from the chemical shift evolution. So how do I get rid of chemical shift evolution? A 180 pulse, right? We worked out the spin echo the other day. So if I put a 180 here in the middle, I'll get rid of the chemical shift evolution during that period. What happens to the J coupling? What does the 180-degree pulse do to the J coupling evolution? Right? If the 180-degree pulse refocused the J coupling just like it does the chemical shift, we won't have gotten anywhere. So we need that pulse, if this is going to work, the 180-degree pulse has to refocus the chemical shifts but leave the J coupling alone. And we'll leave that question open for a little while. The main point of this digression was to make the connection really for the first time since we started talking about the quantum mechanical theory, making a connection between these abstract symbols and what actually happens in the NMR spectrum. So in fact, we could have, right from the beginning, ignored the quantum mechanics and just say, we're going to invent some symbols that we can manipulate, that we invent the rules for manipulating, that will explain the NMR spectra that we see. So we went in the other direction. People took quantum mechanics and used it to explain NMR spectra. But in fact, if we were smart enough, or quantum mechanics hadn't yet been invented, we could have gone the other direction. We could have said, well, we already know that we have a doublet here, so let's invent two symbols. And it could have been that we would have invented symbols yellow or green and red like I did, but eventually we would have decided using colors was too difficult, we need to do something else, and we might eventually have figured that it was good to use this kind of symbols and just to invent a series of rules to manipulate those symbols, and we would have come to the same result without having to know anything about quantum mechanics. That's not the way it happened historically, but it could have. There was no, because our ultimate aim is to connect to properties of the NMR spectrum, it could have happened in either direction. It's just historically the quantum mechanics was laying around waiting for NMR people to use it. So now we can do the one pulse experiment for the coupled spin system. We just have to use all the 4x4 matrices, which is sort of painful. Now our equilibrium density operator consists of the I spin Z magnetization and the S spin Z magnetization. And I've kept of all the terms, all the constants of proportionality that came from the Boltzmann equation, I've only kept the omega there to remind me of which spin I started with. And there's also factors of Boltzmann constant and temperature and H bar really there, but I've not written them. And then we have to work out what we worked out the other day, what the 4x4 matrix looks like for the I spin in the 2-spin case. And then I would do the same thing for the S spin and add the two together to get the equilibrium density operator for the 2-spin system. And then I have to generate, if this is a non-selective pulse, if the pulse is going to affect both spins, then I need to generate the appropriate rotation operator that rotates both spins, the I spin and the S spin. And it's the same game. I do the direct product of the two matrices. It could be, if this is nitrogen and hydrogen, then maybe I'm only pulsing the hydrogens. If I was only pulsing the hydrogens, how do I generate the 4x4 matrix? What would I write here if I was only pulsing the hydrogens and leaving the S spins alone? Pardon? This would be the identity operator, and I'd be doing the direct product of the rotation for the I spin and an identity for the S spin. And if I was doing the reverse, if I was doing a pulse on the nitrogen and not pulsing the hydrogen, then this would be the identity operator here and the rotation operator over here. And you can kind of see, I'm not going to be wanting to do this by hand very often. Right? This is a job for a computer. But I can do the arithmetic, and if I multiply out all the matrices, I end up with this as the result, and then I have to ask myself, what am I looking at here? I multiplied 3 matrices together, I got another matrix, and I have to figure out what it is I have. And I can figure that out, and I got minus IY and minus SY. Of course, we knew that. Z magnetization rotates to the minus Y axis with a 90-degree X pulse. So we should have gotten minus IY and minus SY. That's this matrix, but how would I tell that? Faced with some arbitrary matrix here, how might I figure out what operator I'm looking at? Notice that it turned out to be a linear combination of operators we already know about. And that might suggest to us that we can play the same game that we played with functions earlier. So I end up with some arbitrary operator. Actually, this is the density operator at time t. So I have some arbitrary density operator at time t. I want to know what it contains in some sense. I'll again think of it as a sum over some coefficients. And now a set of basis operators. Before, we were expressing an unknown function in terms of the basis functions. And now we're going to express some operator in terms of some basis operators. And we've been doing this rather trivially without you noticing it, because I've already said, for example, IZ is 1/2 I alpha minus I beta. So I've written this operator as a linear combination of some other operators. So we've already been playing the game without noticing it. So then what do? By the same recipe as before, I want to multiply over here by some other operator. Right, this is what I did before, and then with the functions I integrated and made use of the fact that my basis functions were orthogonal. So when they were integrated, I got delta functions. So now I need to know if I have two basis operators, what do I need to do mathematically so that this is either 0 or 1? 0 if k is unequal to n, and 1 if they're equal to n. So I have no idea, but I can go ask mathematicians that question. And it turns out that what I need to do is take the adjoint of this one, the complex transpose, and then take the trace. Remember, these are matrices, so the trace is the sum of the diagonal elements. It will turn out if we pick our basis operators properly, which means we'll pick the ones that we use all the time in NMR, this will be either 1 or 0. This will be then the delta Kn, or if these aren't properly normalized, times some number. And since we don't like to write the trace all the time, that just uses up extra characters, this will usually be written so this part just takes care of the normalization. It might be 1 if all the basis operators are normalized. So this means the brackets, the straight line here is supposed to mean take the complex transpose over here, make this the adjoint, and then these brackets are supposed to mean the trace. So it's the same kind of notation as the bracket notation for functions. And it was kind of chosen so the typography looks the same, but they mean different things. The bracket notation means take the complex conjugate of the one function, then integrate over all space. Here the notation means take the adjoint of the operator and then the trace operation rather than integration. So again, we have to keep track of whether we're talking about operators or functions. But then when we do this, this side collapses, and we just get C sub k, and if we're not normalized, we'll have bk, bk. You might recall that I said if the operator basis isn't normalized to unity, we still want all the operators to be the same size in some sense, the same normalization constant, even if it's not 1. And that's why here, you can see here, how did I know I wanted b sub k here, rather than b sub n, b sub n? And as long as all the operators have the same norm, it doesn't matter which one I pick here. Because this would be equally true to be c sub k, b sub n, b sub n. Doesn't matter if this is not unity, as long as both of these are the same. If they're not identical, if the operators have different norms, then I'm in trouble trying to figure out what's going on. So then we have a recipe. I have sigma as a result of this calculation, and I ask myself, what's contained in here? Well, if I want to know how much IX magnetization there is, I simply do this. I take the matrix for IX, take its complex conjugate transpose, multiply it by this matrix, sum up the diagonal, and that tells me how much IX magnetization is contained in my density operator. If I do that, I better get 0 because I already know the answer. And then if I want to know how much IY magnetization there is, I multiply by the transpose conjugate of IY, do the multiplication of the matrices, and then sum up the diagonal elements. So I have a recipe for picking out, no matter how messy this matrix looks, I can pick out the coefficients with all the operators as I need to. So now after the pulse, I have free precession. So I have precession under the chemical shift of the I spin, precession under the chemical shift of the S spin, and then the scalar coupling. And because they commute, I can do these one at a time, and I can do them in any order that I would like. So I did it all in one step. I didn't have to. I then took these three matrices and multiplied them together. And here's the 4x4 matrix. So I have, then I take this, do more matrix multiplications. And I end up with this matrix. So then the question is, what do I have here? This is the density operator as a function of time during the acquisition period. And again, I look at that, I'm not so sure what I'm looking at. And now I want to detect. So let's suppose this is a homonuclear system. So I'm going to detect both the I spin and the S spin. They're both hydrogens. And our density, our detection operator was proportional to I plus and S plus. So I need to know what I plus plus S plus is as a 4x4 matrix. That's what it is. So I multiply these two matrices together. And then take the trace. So our recipe for some detectable quantity, right, a measurable quantity, the Boltzmann equilibrium expectation value was the trace of the operator associated with that quantity times the density operator. So we wanted to detect the NMR spectrum. I decided for us that the detection operator was proportional to I plus. So we have to take the trace of I plus S plus in this case, times the density operator. So I multiplied the two together. They have all these terms, but I only care about the sum of the diagonal at this point. So it's a little hard to see what the diagonal is. Here, plus this, plus this, plus this. And here's the NMR spectrum. So we have a signal that's at the I spin chemical shift plus half the J coupling. A signal at the I spin chemical shift minus half the J coupling. So here we go. Here's the S spin chemical shift plus half the J coupling, and the S spin chemical shift minus half the J coupling. So the four components that we knew we would get come out of this kind of a laborious matrix calculation. The different components would be weighted then by the amount of Boltzmann equilibrium magnetization. In this case, they're both hydrogens, so the weighting factors are going to be basically the same. But later on, we'll be able to manipulate the weighting factors in some way. So what did we do? We took the one-spin operators, expanded them up to two-spin operators by this direct product rule, and then did the same matrix calculation that we did for the one-spin case. We took the Boltzmann magnetization, multiplied it by an x rotation by 90 degrees. Let that resulting density operator precess around the z-axis, but now it precessed with both chemical shift and scalar coupling. But at the end of the day, we ended up with a 4x4 matrix. We then multiplied that density operator by our detection operator and took the trace in order to get the free induction decay. If we had 3 spins, the matrices are going to be 8x8. And if we have 4 spins, 16x16. You can see that doing these calculations by explicit matrix operations gets very complicated quickly. You're not going to do it by hand. And in fact, until recently, it was pretty easy to run out of computer memory doing these sorts of calculations for large spin systems. So we would like to get around doing the matrix calculations by hand. So we would like some way to get answers without having to always multiply matrices together, although knowing whenever we need to, we can go back to a computer and multiply matrices to our heart's content. It's a property of human evolution that we're more comfortable with symbols than matrices. It could be that the NMR spectroscopists in another part of the galaxy evolved to manipulate matrices and they find symbols confusing. So they may work in exactly the opposite way that we do. So we want to go on and find a way of doing this by symbols rather than matrices. So we talked about this. How do we resolve the operator components? I kind of jumped ahead a little bit. And we will then use this idea of the expansion of the basis operators to expand the density operator in terms of basis operators. So we can do this at any point. So for example, if we go back to the single spin case, there are 4 possible operators in the basis. So I alpha, remember, was just population of the alpha state. I beta is just population of the beta state. I plus turns beta into alpha. So if we take I plus and multiply it over here, I plus is 0, 1, 0, 0. What is beta? Beta is a column vector with 1 entries. 0, 1. And if I do the multiplication, I get 1, 0. So I plus acts on beta and gives back alpha. And I minus does the opposite. It takes alpha and turns it into beta. These are the quantum mechanical raising and lowering operators. So notice I have a 1 in each of the 4 positions. And that means if I have some arbitrary matrix, I can always write it as this element times I alpha. plus this element times I plus, this element times I minus, and this element times I beta. Okay? If I add these all up, this trivially is equal to this. I can say my density operator for a single spin, my density operator, an arbitrary density operator, is composed of some mixture of I alpha, I beta, I plus, and I minus. You may not like that particular basis. You might say, I'd rather work with Ix, Iy, Iz, and E. But then you can see I can easily convert between the two different bases because Ix is 1/2 of I plus I minus. Right? And that means that if I take 1/2 of these two, I get Ix, and am I missing a factor of 2? That could be I've left out a factor of 2 here. I think this should be this probably needs to be a 2 here. And similarly, Iz is the difference between I alpha and I beta. So I end up with the difference of these terms, and then something that's proportional to the identity. And then we'll usually ignore this, as I said, because the identity commutes with everything. So this idea of expanding an operator in terms of basis operators, if we look at it in this matrix way, right, is really quite simple. They're just saying we have operators that pick out each element in the matrix, and then we can form new combinations of those if we want to. So let's go back to our evolution equation. I probably should have mentioned at some point along the way that the evolution equation for the density operator is called the Liouville-von Neumann equation. And here we have it in terms of sigma. But as we just saw, I can expand sigma in terms of a set of basis operators. So I put in for sigma the sum over the basis operators b sub k with some coefficients, little b sub k, that depend on time. And the same thing over here. And now the basis operators don't depend on time, only the coefficients do. So here I have the time derivative of the coefficients. And now I play the same game. I multiply by the adjoint of an operator b sub j and take the trace. I multiply by the adjoint of an operator b sub j and take the trace. I can do this calculation. Right? This is equal to the delta function times, and picks out only the jth component, times b sub j, the normalization time. So that leads to a differential equation for the coefficients in which I've defined an evolution frequency then as the result of this operation normalized by whatever the normalization constant was. I divided both sides by the normalization constant. If that's 1, that doesn't show up. And we just have this. So this says then that if I have k elements in the operator basis, and we just saw that in for the single spin, we have 3 operators because we don't care about identity. This says that I'll have 3 coupled differential equations. These are arithmetic equations. These aren't operator equations anymore. These are just plain garden variety algebraic differential equations that Mathematica will happily solve for us, in which each coefficient is evolving with some frequency, or frequencies that couple the 2 operators together, and we have a recipe for calculating those frequencies. We have to take the commutator of the Hamiltonian with one of the basis operators, take that answer, multiply it by the adjoint of the other basis operator, and then get the trace. When we do that for our single spin case, and of course this is general now for any number of spins, but if we do it for the single spin 1/2 case, we're going to get back the block equations. The block equations were 3 coupled differential equations for evolution of IZ, IX, and IY magnetization. If I put in as the basis operators here, IX, IY, IZ, I'm just going to get back the block equations. So we've converted the operator equations into a set of differential equations. And I can arrange these then. This just repeats the same thing. I can take these, frequently in the literature, then this symbol will be used for the little b sub j's. This is the expectation value of the operator. So this is meant to be this calculation. Is frequently written like that, just to keep you busy with notation. So this says we have a coupled set of algebraic equations, so we can put them all in matrix format looking like this, where we have an evolution matrix acting on a column vector to give back our new column vector. And again, for the spin 1/2 case, this is just the block equations. But for any number of spins, this just becomes bigger and bigger matrices. But we don't have these operator equations anymore. We just have a set of algebraic first-order equations that Mathematica can solve. But each of these represents, this is a number, but it came from multiplying some matrices together and adding up the trace. And these the matrices might be big. So in our 2-spin case, they're 4x4, then they're 8x8, so on and so forth. There's going to be, the underlying matrices could be huge. But at this point, we've reduced things to a relatively simple algebraic set of equations, or conceptually simple, even though they may be numerically complicated to solve. And this is actually more the picture one thinks of for NMR. We're really thinking about what is happening to the expansion coefficients of the basis operators in the density operator while there's evolution through the pulse sequence. And that may seem a complicated way to think about it, but in fact it turns out to be way, way simpler than the alternative. Let me see. It'd be more fun to actually do a calculation.
Yeah.
So, yep.
Sorry, so I kind of got lost here. Are we calculating now still the time, or we're calculating the frequency or something else?
Well, these are frequencies,
Okay.
and because they're multiplied by I. So everything that's multiplied by I is going to be a frequency. So these are the frequencies, and this, for example, would be some frequency in which the first basis operator evolves. This would be the frequency by which the second basis operator evolves into the first basis operator. So for example, we saw that Ix evolves into 2IYSZ under the scalar coupling Hamiltonian. So this, in fact, if we did the calculation, this might turn out to be JIX here, in which case, and this operator would be Ix, and this operator would be 2Ix IYSZ. So we're going to calculate the amplitude, the time dependence of the amplitudes of each basis operator during the pulse sequence. So it tells us how much of each basis operator there is, and from what I erased, we can associate the different basis operators with the resonance lines in the NMR spectrum. So at the end, we'll read out from the basis operators where the lines are in the spectrum. So, you know, the lingo that people use will frequently say, as I've already said, that the operators evolve. But of course, the basis operators don't evolve. The basis operators are fixed in time. What evolves are the coefficients, the amplitudes of each basis operator's contribution to the density operator. But we'll get tired of using all those words. So I'll say evolution of Ix when I really mean the evolution of the coefficient weighting Ix's contribution to the density operator. We'll come back to this stuff. So this is a helpful shorthand because we like these pictures. So the question is, how do I make these pictures? And here's a rule. So if I have AB, if the commutator of AB is equal to IC, then I can label the axes like this. C on the top, A going to B, and I'll have the recipe then that this is the equation for evolving the operator A. So if I have a set of three, I can't remember how to make those pictures, but I know the operators I'm interested in. I can work out the commutator relationship and then label out this figure, and that will tell me, in my right-handed rule sense, how a set of three operators will evolve. And it, of course, tells you right away if A and B commute with each other, then C, the operator C, can't cause them to evolve. So this leads to a set of rules. And in most NMR spectroscopists, when they start out, have tables of these rules pasted near their desk so they can keep track of them. So what happens, for example, under the chemical shift, Ix rotates around the z-axis towards the plus y-axis. So Ix evolves towards Iy, the Ix gets the cosine term, and Iy gets the sine term. Iy magnetization rotates towards the minus Ix axis in our three-dimensional scheme. So Iy rotates towards minus Ix. Iy gets the cosine, Ix gets the sine. And Iz commutes with Iz, so nothing happens to Iz. So for chemical shift, we have three rules. We just have to apply them over and over again. Scalar coupling, we saw already that Ix rotates towards 2IYSZ. So Ix gets the cosine of the frequency. The frequency in this case is pi jt, or the angle is pi jt. And the 2IYSZ gets the sine part. IY rotates towards minus 2IXSZ. The second term gets the sine component, the first term gets the cosine component. Similarly, if we start on the IXSZ axis, we're going to rotate towards plus IY, so the antiphase term starts to evolve back into the in-phase term. The antiphase term has the cosine component, the in-phase term has the sine component. What does that mean? Again, if we think about the picture we had, the pure antiphase component, again, if I look down from the top, over here I had IYS alpha, and over here IYS beta. Remember, this was rotating this way, this was rotating this way. That was the special moment where they were opposed. And now what happens as time goes on? As time goes on, a little while later, right, this one points here, this one points here. And if I resolve them into components, the projection down here is how much antiphase magnetization is left. And the projection here is how much in-phase magnetization I have. Because the projection back onto the minus x-axis, both of those two components are pointing in the same direction, and they say they have the same magnitude by symmetry. So that's the in-phase component. And the antiphase component are the projections onto the y-axis. And as time goes on, right, as these come up here, we're going to have more and more of the in-phase component, less and less of the antiphase. And eventually we'll have the in-phase component, but it'll be upside down relative to what we started with. And if we turned on the receiver at that point, we would see the doublet, but it would be upside down. Because now the in-phase doublet points along the x-axis, minus x-axis. So this is just, these rules are just reflecting that. The two magnetization components are opposed here, but as they start to rotate, you have a projection onto the orthogonal axis in which they're both in the same direction, and that reflects some in-phase magnetization that then goes in. And again, Z commutes with Z, so the scalar coupling doesn't affect the Z operation. And then we have pulses, again, that rotate. Z, the next pulse rotates Z magnetization towards the minus y-axis, so on and so forth. So we have a set of rules about the pulses, and that's it. These three slides are for solution NMR, the only rules. Yep?
What about the frequency?
Under the scalar coupling, under chemical shift. So remember, we do each bit, we can do each bit independently. So if we have something like this, under the chemical shift Hamiltonian, first we can do omega I, SZ, or IZ, and this will give 2, and the IX operator turns into so I've just applied the rule to the IX operator because the shift precession here only affects IX. And the other bits just come along to the right. And now I can apply the S evolution, but SZ commutes with SZ, so nothing happens, and I end up with 2 IX SZ cosine omega I t plus 2 IY SZ sine omega I t. if I had double quantum, if I had something like 2, we haven't talked about these yet. Suppose I had this under the scale, under the chemical shift. So it doesn't matter which order I do them because the I and S spins commute. But if I did the I spin first, I would then end up with 2IX cosine omega I t plus IY sine omega I t. And then, well, let's do both of them. And then I do this one, and so I would get times sy cosine omega st. And now sy will rotate towards minus sx, and I'll have minus sx sine omega st. And then I can just multiply these all out and end up with 4 terms with various combinations of sines and cosines.
So how can we draw like the magnetization? Like the vector. So can we draw
Not so easily. And that's related, that's interesting. Let's leave that for next time. But I'll let you puzzle, since you're going to make me puzzle about a vector picture for this. I'll let you puzzle. What happens for a term like this for the J coupling? I did the chemical shift for you. You can wonder what happens, what does evolution under the J coupling look like for that? None of my pictures showed that, right? I didn't show any pictures of those kinds of operators. This could give you a hint, and I'll give you another hint for thinking about it. If you go back and look at the energy levels for the 2-spin system, we do a lot of things with the operators and this complicated mathematics, but sometimes it's useful to just go back and look at the energy levels. So answering this question about how does multiple quantum coherence evolve under the scale of coupling, you can get at either with this picture or by going back to the energy levels and thinking about the energy levels. So I'll puzzle about your question and you can puzzle about my question. Now, unfortunately, the provost, we should have a problem session, but unfortunately the provost has called me to a meeting at 3 o'clock. He's been ignoring the fact that on my calendar it says problem session. He apparently thinks problem session means me dealing with his problems rather than us having a problem session for the course. So I'll try to explain to him that problem session at 3 o'clock does not refer to anything he's interested in, and try to get him to stop calling 3 o'clock meetings on Thursday. So I apologize. But now I'll post another problem set anyhow and an answer key for problem set 1.
Oh, that's why you had to use that today. I didn't know whether to move the switch on the camera. I didn't want to start messing with the way you had it set up. I should have interrupted you, I guess. So,
Before you came,
good. That's what I want to do. Yeah, good one.